Good morning, everyone. Since we already have knowledge about the basics of surveying, leveling, measurement of angles and direction, transverse surveys, let us proceed to Unit 5, which is Topographic Survey. My name is John Gabriel Amanlangit. Here with me to discuss to you about topographic surveyings are Dongog Jason, Lee Ranito, and Mata Rafaela, and we are the group Sheesh. Here is the discussion content that will be discussed in the video, starting with introduction to topographic survey, which will be discussed by me, contours, which will be discussed by Ella, topographic mapping, which will be discussed by Jason and Renito. Introduction to topographic surveying. First, let's start with sugarloaves. These are idealized depictions from a side or oblique view. The only form of topography on early maps due to the lack of detailed surveying. It gives location of mountains or hills, but not the precise size. Hatchers. I will talk about its disadvantages and advantages. Hatchers will be discussed thoroughly by the next reporter. Let's start with its disadvantages. It has a lack of absolute information, difficulty in distinguishing the direction of the slope, it is time-consuming to produce, and obscures other information. Not very effective except in mountainous terrain. Advantages is they may show minor but important details, otherwise lost on the contour map within the contour intervals. Contours, its advantages and disadvantages. Let's start with the advantages. It is the most comparable method. It is the origin for many newer depiction techniques and it is now familiar to many users. Its disadvantages are it is an abstract method, poorly suited to small scales. It is less imaginable but depending on contour interval, map scale, landscape type, and user's experience. Next, we have the advantages and disadvantages of hyposymmetric tints. Its advantages are highly imageable, continuous in appearance, can show gender detail and character of landscape, suitable over a variety of scales and as a general background for a variety of map types. Its disadvantages are manually required artistic creation with pencils or airbrush. It, it is costly and often poorly rendered when done manually. It creates a variable background with some slopes very dark. Next, we have shaded relief. Its advantages are adds imageability, mostly at small scale, easily applied and understood. Its disadvantages are exaggerated terrace effect, no new real information is added, differential contrast between tints and other elements, W's color associates, which color scheme, chroma of the same hue or spectrum range, green, yellow, and red. Next, we have block perspective diagrams. Its advantage is it's the most imageable, portrayable of landscape, often used for ski hills and panoramas. Its disadvantage is the most time-consuming to produce with no consistent linear scale.
Now we move on to more discussions about contours and its different types and characteristics. So again, an overview of what a contour is. It is an irregular shape or unbroken line used to map out areas with the same elevation in a topographic map. These lines cannot be seen in nature and is just used to create an idea on a terrain's elevation. We're discussing this more in depth because this is the most common method of representing the topography of an area. So when we get into doing our practices, our engineering practices, this is probably the kind of map that we will be dealing with most of the time. To give you a clearer picture of how the contour lines represent areas of a terrain. So as you can see in the first example, where the terrain has two bumps on each side, The smaller the contour line is, or the more enclosed it is by other contour lines, the steeper it gets. You can see that in the second example, where there is only one single point of elevation, or one continuous point towards an elevation, and that gives us just a very pointy mountain. On the third example, we can see that there are two contour lines that are similar in size, and that is also translated as two very similarly elevated areas in a map. On the second slide of examples, we can see here that on the first example and in the second example, the closer the contour lines are together, the steeper it gets. And the more, or the farther they are, the smoother the slope is. On the third example, it's the same as before, where two similarly sized contour lines are of the same height. Now we move on to the types of contours. The first one being index contours, a contour line that is 2 times thicker than a normal contour and carries with it the number or elevation designation. This contour line is normally shown in every 5th contour. So as you can see in the topography map picture provided, you can see these thick lines having numbers on them, having 1,300, 1,200, 1,100, and these measurements are usually in meters. Moving on to intermediate contours, these are found in between index contours. These contours normally don't have a label unless the terrain is relatively flat. It is shaped according to the contour interval of the map. We will discuss more about the contour interval later on in the video. In situations where intermediate contours may merge due to being too close to each other, it is customary to omit or delete the lines for short distances for readability. Omitting these lines or deleting the lines for readability is also called feathering. Next is supplementary contours. These are contour lines used in very flat terrain or when intermediate contours are too far apart. These contour lines are usually presented as dotted lines and are placed at 1/2 of the contour interval of the map. 1/2 making it in the middle of intermediate contours. Next is depression contours, contour lines used to represent low spots near the line. These lines are usually represented as lines with ticks on the side where depression is observed. To give you a clearer image of how these ticks define depression, there are 2 ways of doing this, which is either the ticks are going towards each other or the ticks are going towards the same direction. So first, if it goes towards each other, then that means that that is the only area where the depression takes place. As for when the ticks face the same direction, it means that there is a continuous depression going towards the middle of that area. For the last type of contour, it is called the approximate contour, and it is also referred to as the indefinite contour. These are contour lines that cannot be drawn clearly because of limitations in the study, and they are solely based on an educated guess by the maker of the map. The next thing that we need to tackle about is the contour interval. So this is the constant vertical distance between 2 adjacent contour lines. The value for the contour intervals are usually multiples of 0.5, 1, 2, 5, 10, 20, 50, and 100 meters. The contour interval must also suit the area being mapped. Smaller intervals for smaller hills and slopes, while larger intervals for mountainous areas. As for examples of these contour intervals, you can see that in the map, it is plotted down as 1,100, 1,200, 1,300, and 1,400. So just by looking at this reference, we can say that the contour interval is 100 meters. Another example, we can see that the map view is 1,500, while it's labeled for its side view that the elevation goes from 1940, 1860, 780, 1700, and so on and so forth, just a quick and simple subtraction would give us an elevation or a contour interval of 80 meters or 80 feet, I guess. Now that we've learned what a contour interval is, we have to now learn the selection of a contour interval, or the things that you need to consider to decide on what value you want your contour interval to be. First is the relative cost. Since the more accurate or small the contour interval is, the more expensive the topographical map. Next is the purpose of the map. Do you need highly detailed information of the area, or just a general overview of the elevations? Next is the nature of the terrain. Is the area flat? Are there small hills, tall mountains? And lastly, the scale of the map. How big of an area is covered, or how big do you want your topographical map to be? Lastly, about contours is its characteristics, or things that have to always be true when it comes to contour lines. So first, are all points on any one contour have the same elevation? Second, every contour closes on itself, either within or beyond the limits of the map. The closure may occur within the mapped area, but often happens outside the area, and thus will not appear on the map sheet. Third, contours on the ground cannot cross one another except where an overhanging cliff, a vertical ledge, or wall is represented on the map. Number 5, contours are evenly spaced on a uniform slope. 6, contours are straight and parallel to each other on a plane surface. 7, irregular contours signify rough and rugged terrain. Number 8, the closer the contours, the steeper the slope. Number 9, contours cross curves and a crowned sloping street in typical U-shaped curves. Basically, roads are represented as U-shaped curves. Number 10, contours cross streams in a V pattern pointing upwards. So, the direction of the stream is usually opposite to the V formation. Number 11, a contour which closes within the limits of a map indicates either a summit or a depression. That is all for contours. Thank you.
There are several rules in viewing topographic map, like rule of V's, which usually refers to having contour pointing uphill, which indicate that there is a valley or stream. Another rule is rule of O's, which indicates that the highest area as the innermost part of the loop and downhill on the outer area. And space contour, which refers to close contour, which indicate a steep slope, distant contour, which indicate a shallow slope, and if two or more contour lines merge, indicates a cliff. There are two methods in locating contour: direct method and indirect method. In the direct method, the contour to be plotted is actually traced on the ground. Points which happen to fall on a desired contour are only surveyed, plotted, and finally joined to obtain the particular contour. This method is slow and tedious, thus used for a large-scale map, small contour intervals, and at a high degree of precision. While indirect method, the spot level and selected guide points are taken with a level and their level are computed. The horizontal point of these points are measured or computed, and the points are plotted on the plan. The contour are then drawn by the process called interpolation of contours from the level of the guide points. For indirect method, there is a method called coordinating square or grid method. In this method, the area to be surveyed is divided into a grid or series of squares. The grid size may vary from 5 meters by 5 meters to 25 meters by 25 meters, depending upon the nature of the terrain, the contour interval required, and the scale of the map desired. Also, the grid may not be of the same size throughout, but may vary depending upon the requirement and field condition. The grid corners are marked on the ground, and spot level of these corners are determined by leveling. The grid is plotted to the scale of the map, and the spot levels of the grid corners are entered. The contour of desired value are then located by interpolation. This method is used for large-scale mapping and at a average precision.
So now we will be discussing about the construction of contours. The basic method of constructing contours is applied to each grid cell. We use linear interpolation to find the location of the contour interval. So first of all, we check all four sides of a grid cell to see if there are any contour interval between two intersections of the grid cell. After that, we apply linear interpolation to all sides with interval to locate the contour interval. As shown in the given problem below, we have a contour map which needs a 5 feet contour interval, and each grid cell has a dimension of 80 feet by 100 feet. And if we look closely at the given map, we can see that the lowest point is 98 and its highest point is 119. And knowing that the interval of each contour is 5 feet, we get 100, 105, 110, and 115 as our interval. Let's take the upper left grid cell for an example. We can see that it has a contour interval in each of its sides. So, let's solve for the upper edge of the grid cell. First thing we're going to do is find the height difference, which we get by subtracting 102 to 98, which we get 4. Then, given that the horizontal dimension of the grid cell is 100 feet, we divide 100 with our height difference, which gives us 25. Then after that, we take our contour interval of 100 and subtract it with the lowest value of the line, which is 98, which we get 2. Then after that, to get the point location of the interval, we multiply 25 by 2, which we got from subtracting the contour interval with the lowest value of the line, in which we get 50 feet. After that, we plot it on the map by measuring 50 feet from the intersection point 98, since it has the lower value. Next, let's solve for the lower edge of the grid cell. First we're going to do is find the height difference, which we get by subtracting 108 to 101, which we get 7. Then given that the horizontal dimension of the grid cell is 100 feet, we divide it with our height difference of 7, which gives us 14.29. Then after that, we take our contour interval of 105 and subtract it with the lowest value of the line, which is 101, we get 4. After that, to get the point location of the interval, we multiply 14.29 by 4. We get 57.15. After that, we plot it on the map by measuring 57.15 feet from the intersection point 101. Next, we're going to solve for the left edge of the grid cell. First we're going to do is find the height difference by subtracting 101 to 98, which we get 3. Then, given that the vertical dimension of the grid cell is 80 feet, we divide it with our height difference of 3, which gives us 26.67. Then after that, we take our contour interval of 100 and subtract it with the lowest value of the line, which is 98, which we get 2. Then after that, we get the point location with the interval by multiplying 26.67 by 2. We get 53.54 feet. After that, we plot it on the map by measuring 53.34 feet from the intersection point 98. And lastly, we will solve the right edge of the grid cell. First thing we're going to do is find the height difference by subtracting 108 to 102. We get 6. Then given that the vertical dimension of the grid cell is 80, we divided 80 by 6, which gives us 13.33. After that, we take our contour interval of 5 and subtract it with the lowest value of the line, which is 102. We get 3. After that, to get to the point location of the interval, we multiply 13.33 by 3. We get 40 feet. After that, we plot it on the map by measuring 40 feet from the intersection point 102. And finally, after plotting all the points, we connect all points of similar intervals. Then, repeating the same steps shown before, with the remaining 8 grid cells, we get this. And that is all for the construction of contours. Thank you for listening.